Hello students, in the previous session we introduced ourselves to the three-dimensional geometry. We also looked into the coordinate planes and how to represent a point in a coordinate system when it is three-dimensional. Today we shall look into the distance formula, that is to find out the distance between two points in three-dimensional space. The distance between points P x1, y1, z1 and q, that is x2, y2, z2 is given by pq is equal to square root of x2 minus x1 whole square plus y2 minus y1 whole square plus z2 minus z1 whole square. Here if O is the origin and P x, y, z is a point in space, then OP is equal to square root of x minus 0 whole square plus y minus 0 whole square plus z minus 0 whole square, which can be simplified as square root of x square plus y square plus z square. Now, let us look into an example. Find the distance between the points P minus 2, 4, 1 and Q 1, 2, minus 5. Here we can see that x1 is minus 2, y1 is 4, z1 is equal to 1, x2 is 1, y2 similarly is 2 and z2 is minus 5. Now, on substituting in the distance formula, we have PQ is equal to square root of x2 minus x1 whole square plus y2 minus y1 whole square plus z2 minus z1 whole square. On substituting the values, we have square root of 1 minus 2 whole square plus 2 minus 4 whole square plus minus 5 minus 1 whole square, which on simplification gives square root of 9 plus 4 plus 36, which is equal to square root of 49 and that is equal to 7 units. Let us look into one more example. Find the coordinates of a point on y axis which is at a distance of 5 square root 2 from the point P 3, minus 2, 5. Now, let the point be A, that is 0, y, 0, which is on y axis. Then we are also given that AP is equal to 5 into square root 2. So, using our distance formula, we have here square root of 0 minus 3 whole square plus y plus 2 whole square plus 0 minus 5 whole square is equal to 5 square root 2, which on simplification gives us 9 plus y plus 2 whole square plus 25 is equal to 50. This we have obtained by squaring both the sides, which on simplification again gives us y plus 2 whole square is equal to 16. On taking square root on both sides, we get y plus 2 is equal to plus or minus 4, that is y is equal to either 2 or negative 6. Hence, the coordinates of the required point are 0, 2, 0 and 0, minus 6, 0. Let us look into one more interesting example here. Determine the point in xy plane which is equidistant from 3 points, namely A 2, 0, 3, B 0, 3, 2 and C 0, 0, 1. We know that the z coordinate of every point on xy plane is 0. So, let P x, y, 0 be a point on xy plane such that PA is equal to PB, that is equal to PC. Let us first take PA is equal to PB. On squaring both sides, we have P A square is equal to P B square. On substituting in the distance formula, we obtain x minus 2 whole square plus y minus 0 whole square plus 0 minus 3 whole square, that is equal to x minus 0 whole square plus y minus 3 whole square plus 0 minus 2 whole square. On simplifying, we obtain the equation as 4x minus 6y is equal to 0. We can find 2 as a common factor here, and thus we can simplify this equation as 2x minus 3y is equal to 0. Take this equation as first equation. Now, let us consider Pb is equal to Pc. Similarly, on squaring both sides, we can write it as Pb square is equal to Pc square. On substituting in the distance formula, we have an expression here x minus 0 whole square plus y minus 3 whole square plus 0 minus 2 whole square is equal to x minus 0 whole square plus y minus 0 whole square plus 0 minus 1 whole square. On simplifying, we get an expression as minus 6y plus 12 is equal to 0, which on solving gives us y is equal to 2. Take this as second expression. Putting y is equal to 2 in equation 1, we obtain x is equal to 3. Hence, the required point has the coordinate 3, 2, 0. Let us look into one more interesting example here. Show that the points A 0, 1, 2, B 2, minus 1, 3 and C 1, minus 3, 1 are vertices of an isosceles right angle triangle. Now, using distance formula, we will first obtain the distances of lengths AB, BC and CA. Look here, when we calculate AB using distance formula, we have square root of 2 minus 0 whole square plus minus 1 whole square plus 3 minus 2 whole square, which on simplification gives square root of 4 plus 1, that is square root of 9, which is equal to 3. Similarly, BC is equal to square root of 1 minus 2 whole square plus minus 3 plus 1 whole square plus 1 minus 3 whole square, that is equal to square root of 1 plus 4 plus 4, which is again equal to square root of 9, that is 3. CA is equal to square root of 1 minus 0 whole square plus minus 3 minus 1 whole square plus 1 minus 2 whole square, that is equal to under root of 1 plus 16 plus 1, which gives us square root of 18, that can be written as 3 square root 2. What do you observe here? Clearly, AB is equal to BC. What does it imply? It is an isosceles triangle. We also can verify here that AB square plus BC square is equal to AC square. Hence, our triangle ABC is an isosceles right angle triangle which is right angled at B. One more example here. Find the locus of a point which is equidistant from the points A 0, 2, 3 and B 2, minus 2, 1. Let P x, y, z be any point which is equidistant from A 0, 2, 3 and B 2, minus 2, 1. Then PA is equal to PB can be expressed as PA square is equal to PB square, that is by squaring on both the sides. By using distance formula, we can obtain x minus 0 whole square plus y minus 2 whole square plus z minus 3 whole square is equal to x minus 2 whole square plus y plus 2 whole square plus z minus 1 whole square, which on solving can be reduced to 4x minus 8y minus 4z plus 4 is equal to 0. As we can see here, 4 is common and we can reduce it to x minus 2y minus z plus 1 is equal to 0. Hence, the required locus is x minus 2y minus z plus 1 is equal to 0. Now, let us introduce ourselves to the section formula. Let us take points P x1 y1 z1 and Q x2 y2 z2 be 2 points in the space, and let R be a point on the line segment joining P and Q such that it divides the join of P and Q internally in the ratio m1 is to m2. Then the coordinates of R are given by m1 x2 plus m2 x1 upon m1 plus m2, comma m1 y2 plus m2 y1 upon m1 plus m2, comma m1 z2 plus m2 z1 upon m1 plus m2. This is the formula we will be using as section formula. We can see in the figure here, we have got x axis, y axis and z axis, and we can see the line PQ. P is given by the point x1 y1 z1 and Q point is x2 y2 z2, and R is the point which is dividing PQ in the ratio m1 and m2, and the coordinates are given by x, y, z. We have an important remark to make here. If R is the midpoint of the segment joining P x1, y1, z1 and Q x2, y2, z2, then m1 is equal to m2 is equal to 1, and so the coordinates of R are given by x1 plus x2 upon 2, comma y1 plus y2 upon 2, comma z1 plus z2 upon 2. And another important remark here, if P point x1, y1, z1 and Q x2, y2, z2 be 2 points, and let R be a point on PQ produced dividing it externally in the ratio m1 is to m2, then the coordinates of R are m1 x2 minus m2 x1 upon m1 minus m2, comma m1 y2 minus m2 y1 upon m1 minus m2, comma m1 z2 minus m2 z1 upon m1 minus m2. Now, let us solve an example to understand the application of section formula for the internal as well as external division. Find the coordinates of a point which divides the join of point P 2, minus 1, 4 and Q 4, 3, 2 in the ratio 2 is to 3. First is internally and second is externally. Now, let R x, y, z be the required point. If R divides PQ internally in the ratio 2 is to 3, then by using our section formula, we can obtain the coordinates of x point as 2 into 4 plus 3 into 2 upon 2 plus 3, y coordinate as 2 into 3 plus 3 into negative 1 upon 2 plus 3, and z coordinate as 2 into 2 plus 3 into 4 upon 2 plus 3, which on simplification gives us the value of x as 14 upon 5 and y as 3 upon 5 and z is equal to 16 upon 5. So, the coordinates of point R are 14 upon 5, 3 upon 5, 16 upon 5. Now, let us look into the division externally. If R divides PQ externally in the ratio 2:3, then the coordinates of x are 2 into 4 minus 3 into 2 upon 2 minus 3, and coordinates of y are 2 into 3 minus 3 into negative 1 upon 2 minus 3, and coordinates of z will be 2 into 2 minus 3 into 4 upon 2 minus 3, which on simplification gives us the value of x as x is equal to minus 2, y is equal to minus 9 and z is equal to 8. So, the coordinates of R are minus 2, minus 9, 8. Now, let us look into one more example. Find the ratio in which line joining the points 1, 2, 3 and minus 3, 4, minus 5 is divided by the xy plane. Also, find the coordinates of the point of division. Look into the solution. Suppose the line joining the points P 1, 2, 3 and Q minus 3, 4, minus 5 is divided by the xy plane at a point R in the ratio k is to 1. Then the coordinates of R will be given by minus 3k plus 1 upon k plus 1, 4k plus 2 upon k plus 1, minus 5k plus 3 upon k plus 1. Take this as the first equation. Since R lies on xy plane, that is z is equal to 0, therefore, we can equate it to as minus 5k plus 3 upon k plus 1 is equal to 0, which on solution will give us k is equal to 3 upon 5. So, the required ratio is 3 upon 5 is to 1 or 3 is to 5. Putting k is equal to 3 upon 5 in 1, we obtain the coordinates of R as minus 1 upon 2, 11 upon 4, 0. Let us look into one more example here. Using section formula, prove that the 3 points A 2, 3, 5, B 1, 2, 3 and C 7, 0, minus 1 are collinear. Suppose the given points are collinear and C divides AB in the ratio k is to 1, the coordinates of C are k minus 2 upon k plus 1, 2k plus 3 upon k plus 1, 3k plus 5 upon k plus 1. But coordinates of C are given as 7, 0, minus 1. Therefore, we can equate them and obtain k minus 2 upon k plus 1 is equal to 7. Similarly, 2k plus 3 upon k plus 1 can be equated to 0 and 3k plus 5 upon k plus 1 can be equated to negative 1. From each of these equations, we obtain the value of k as minus 3 upon 2. Since each of these three equations give the same value of k, therefore, the given points are collinear and C divides AB externally in the ratio 3 is to 2. So, students, today we discussed about the distance formula, that is to find out the distance between 2 points, and we also discussed about the section formula to divide the line segment internally as well as externally. We shall look into some more interesting examples in the next session. Thank you.